Finite Math Chapter 8, Section 1, Sets. So what is a set? Well, think of it as a well-defined collection of objects. An example would be the set of all U.S. coins, or the set of all students in finite math class. Now, some poorly defined sets would be the set of all young adults. What exactly constitutes a young adult? You need to define that in order to actually have a good set. The set of all students with good grades. What constitutes a good grade? That could vary from student to student. So neither of these two meet the criteria of being well defined. In math, we're usually going to have sets that are groups of numbers. The elements that make up sets are separated by a comma and they're enclosed in braces. And braces are like the little squiggly bracket things. For example, the set of odd numbers between 1 and 10 would look like this. The numbers, or whatever, that belong to the set are called elements or members. And when we want to show that an element belongs to a set, we use the symbol that you see here. And if we want to indicate that it does not belong to a set, we use the same symbol with a slash through it. So for example, in this, we read this symbol right here as 3 is a member of or is an element of the set 1, 3, 5, 7, 9. 2 is not a member of or is not an element of the set containing 1, 3, 5, 7, and 9. Sets are usually named by a capital letter, so we give it a name so we don't have to rewrite it every time we want to talk about it. For example, our set of 1, 3, 5, 7, and 9, we can give the name B, and then we can just say 2 is not a member of B, rather than having to rewrite the set. If a set has no members, it is called the empty or the null set and is represented by a 0 with a slash through it. The empty or null set has absolutely no members in it, and you want to be careful. Don't designate it as a set with 0 in it, because that is not empty. It has 0. For example, the set of all juniors in finite math class, at least this year, would be the empty set. Two sets are equal if they contain the exact same elements, and you can also use set builder notation to describe a set. And here's an example. X such that X has the property of P. Okay, so for example, using a real set we've been working with, X such that X is an odd number between 1 and 10. Really how you read it is the set of all elements X such that X is an odd number between 1 and 10. Okay, here's a couple of examples to try. See if you can find the elements belonging to the given sets. There's 2 questions here. I'll show them to you one at a time. Pause in between, try the answer out, then you'll see the answer when you resume, and then the next question. Okay, so the natural numbers less than 5 would be 1, 2, 3, and 4, and states that border Florida would be Alabama and Georgia. The universal set for a particular discussion is the set that contains all of the objects being discussed. For example, it might be all of the students in the school or all the states in the U.S. Here's another example. In elementary math, the set of whole numbers might be the universal set, while in college algebra, it might be the set of real numbers. When it's necessary to consider the universal set, it will either be stated or it'll be clearly understood from the context of the problem. Like a word problem, you'd have a pretty good idea what the universal set would be. Now, sometimes every element of one set also belongs to another set. For example, let's say A is 3, 4, 5, 6, and B is 1, 2, 3, 4, 5, 6, 7, 8. Then every element that's in A is also in B, and A would be called a subset of B. So A is a subset of a set B, and it's written with this symbol here. It's kind of like a sideways U with a line under it, provided that every element of A is also an element of B. So try this example, and pause the recording to do it, and then resume the recording to see how you did. Okay, for A, M is the set of all businesses making a profit in the last calendar year, and N is all set of businesses. Well, each business making a profit is a business. It would be in the set of N, so M is a subset of N. For part B, M is the set of all first-year students at a college at the end of an academic year. N is the set of all 18-year-old students at the college at the end of the academic year. Well, at the beginning and end of an academic year, some first-year students are older than 18. Some start college later. So there are parts of M that are not included in N, so M cannot be a subset of N, and you would write that using the subset symbol with a slash across it. Now every set A is a subset of itself, because every element in A is also an element of A. The empty set is a subset of every set. So the empty set, just because it has nothing in it, it's actually a subset of everything. So for any subset A, here's how we put this in the symbolism we've been talking about. The empty set is a subset of A, and A is a subset of A. Now, a set A is said to be a proper subset of B, and if every element of A is an element of B, but B contains at least one element that's not a member of A. Okay, I know that may have sounded a little confusing. Let me try to sort that out. Okay, let's say you have a set A, and every member of set A is also in set B. But B actually has other members as well. So B is actually a larger set. And A does not have everything that's in B, it just has some of the things. In that case, A would be considered a proper subset because it's not identical to B, it just contains some of the elements. It's made up of some of the elements of B, but not all of them. And notice there's a slightly different symbol for that. We use the subset without the line underneath. And again, that's called a proper subset. Okay, in these two examples, you're going to decide whether or not E is a subset of F. Pause the recording, give it a try, and resume the recording to see how you did. Okay, the first one's pretty straightforward. It's easy to see. Everything in E is contained in F, and F actually contains more than just what's in E. So, E is indeed a proper subset of F. B is a little bit harder because you got to think about it a little bit more. E is the set of registered voters in Texas. F is the set of adults aged 18 years or older. Now, to be registered to vote, you do have to be 18. So, the members of set E are going to be in set F. All of the members of set E are going to be in set F because they have to be 18 or older. But all those who are 18 or older are not registered to vote. So F will contain elements that are not part of E. So this means that E is indeed a proper subset of F. Everything in E is contained in F, but F also has additional elements that are not a part of E. All right, one more. E is a set of diet drinks. F is the set of diet soda drinks sweetened with NutraSweet. Decide whether this is a proper subset. Pause the recording if you need to and resume to check your answer. Okay, some diet soda drinks are sweetened with sugar, other sugar substitutes like Splenda, or even the few are still around that are sweetened with saccharin. So in this case, E is not a proper subset of F. Actually, it's not even a subset of F. It's kind of a backwards relationship. F should be considered a subset of E. So the answer to this one is no. E is not a proper subset of F. Now we're going to list all the possible subsets for each of the given sets. And this can be a little bit involved, so pause the recording if you need to, give this a try, and then resume the recording to check your answer. So for A, we have the set 7, 8, and what they do is they're using a tree diagram, which is kind of a way of listing the subsets of the given set. And it shows us that there are 4 subsets. What they're doing is they're taking each number, they start with 7, and you have two possibilities. It's either in the subset or it's not. So you have yes and you have no. And then for each branch for 7, they create 2 more branches for the number 8. And they basically have the same thing. It's either in the subset or it's not. And then at the end, you kind of put all that together. So we have a subset where 7 and 8 are both members. And then one where 7 is and 8 isn't. And then one where 7 is not and 8 is. And then you have one where neither 7 nor 8 are members, and it's the empty set. So we have 4 possibilities: 7, 8, 7, 8, and the empty set. Okay, this one had 3 elements, so a little bit longer, but we did the same thing. And notice for each, we're answering, is this in the subset with either yes or no? And you can see we did the same thing. We just had to have another set of branches for C. And this time we have, I believe it's 8. 1, 2, 3, 4, 5, 6, 7, 8 subsets. We have the empty set. We have the sets that contain just one of each, A, B, and C. And then we have all the possible combinations of 2 of those 3. And then finally the subset that equals the original set. Now, as we're doing this, I pointed out that there are 2 possibilities for each element. It's either in the subset or it's not. In our example, when we had a set with 2 elements, there were 4 subsets. And notice that 2 to the second is 4. In our set with 3 elements, we had 8 subsets, which, by the way, is 2 to the third. Now, we could keep doing examples and increasing set size, and if you want to test this statement here, you can do that, but they would all lead you to this conclusion, that a set of n distinct elements has 2 to the n subsets. In other words, if you have a set with 5 elements, you can make 2 to the 5th subsets. If you have a set with 10 elements, you can have 2 to the 10th subsets. Okay, let's try this example. You're going to find the number of subsets for each of the given set. Pause the recording, give this a try, and resume the recording to check your answer. Okay, we have 4 elements, 2 to the 4th, 16 subsets. Part B, X, all elements X, such that X is a month of the year. There are 12 months in the year. 2 to the 12th, 4,096 subsets. And part C, a little tricky. Since the empty set has 0 elements, though, it has 2 to the 0, or 1 subset, which is the empty set itself. All right, let's talk Venn diagrams for a minute. Venn diagrams can be used to illustrate relationships among sets. This is an example of a Venn diagram. It shows a set A that is a subset of B. How I know it's a subset is A is contained entirely inside of B. The areas of the regions are not meant to be proportional to the size of the corresponding sets. So if you think, well, it looks like A is about half the size of B, that really doesn't mean anything. It doesn't mean it contains half of the elements. They're not meant to indicate proportion. The rectangle surrounding the circles is to represent the universal set U. When you're listing the elements of a set with an infinite number of members, this is a little side note here, you use the 3 dots or the ellipses to indicate that the pattern of numbers continues infinitely. For example, and we've done this before, when we want to indicate the set of integers, this is how we'll often list it. Okay, some operations on set. There's several things you can do with sets. Given a set A and a universal set U, the set of all elements of U that do not belong to A is called the complement of A and is written as A with like a little dash called A prime. Over here we've got a set called B, and then everything outside of B that doesn't belong to B is called B prime. Now please don't confuse this with Optimus Prime, who is in fact a transformer. Okay, so some examples. A is a set of all female students in this class. U would be the set of all students in this class. then A prime would be the set of all male students in this class. You may sometimes in some textbooks see the A prime written as A with a line over it. The meaning is the same, it's interchangeable. Okay, so try this out. Work this example, pause the recording to do it, and resume the recording to check your answer. Okay, A prime would be all the elements of U that are not in A. So that would be 2, 4, and 6. B prime would be 1, 2, 5, and 7. And the empty set prime would be U, and U prime would be the empty set. And that would be true regardless of what A and B contained. And now we're going to talk about the intersection of two sets. If you're given two sets A and B, the set of all elements belonging to both set A and set B is called the intersection. And here you have it pictured as in a Venn diagram. The shaded blue area would be the intersection. And you note the symbol looks kind of like an upside down U. It means A intersection B. For example, let A be 1, 2, 4, 5, 7, and B is 2, 4, 5, 7, 9, 11. 2, 4, 5, and 7 are all elements that belong to both set A and set B. So the intersection of A and B is 2, 4, 5, and 7. Now you try these two examples, pause the recording to do it, and then resume the recording to check your answer. Okay, again, A, pretty straightforward. It's easy to see. 15 and 25 are in both sets, so 15 and 25 would be the intersection. Part B is the empty set. No teenager is also a senior citizen, so there is no intersection between the two sets. And we can also have sets that are called disjoint, and those are sets with no elements in common, kind of like example B, the example we just did. Being a teenager and being a senior citizen, those two sets would be disjoint. This is how they would be depicted using a Venn diagram. And it says that for any sets A and B, if A and B are disjoint sets, then the intersection of the two is the empty set. There's nothing in the intersection. The union of sets, the set of all elements belonging to set A or to set B or both, is called the union of the two sets and is symbolized as A union B. And you'll notice the little union symbol looks like a U, so that's kind of easy to remember. And then just remember for intersection, you flip it over. Okay, the union of these two sets would be the blue area. If A is 1, 3, 5 and B is 3, 5, 7, 9, then A or B, which would be A union B, would be the union of the two sets, which is 1, 3, 5, 7, 9. Now, you got to be a little bit careful when you're dealing with sets because it can get kind of confusing with the word or. In English, when I say you can have an ice cream or a cookie, the idea is that you can have one or the other, but not both. In set theory and in probability, when we use the word or, we mean one, the other, or both. So both is perfectly acceptable with the word or when we're talking about union sets, union of sets, or when we're talking about sets. The word and is used in sets and in probability to indicate an intersection. Now, if I were to say in English, you can have an ice cream and a cookie, the idea is that you get both of them. When we say and in sets and in probabilities, the idea is the intersection, that you have to have both of them at the same time, and you only want where they meet. You don't want anything where they don't meet. Okay, this is just a summary of what we've been talking about. We've got complement, intersection, and union described and illustrated, and then also written in set builder notation. You might want to take a minute and pause and look over that and make sure you've got it down, and then move on and we'll do some examples. Okay, the rest of this recording is just some extra practice problems. Try them out, pause the recording as you do so, and then resume to check your answers, and proceed like this until the recording is finished.